look at regression. What are the key concepts? If the value of the correlation coefficient is significant, determine the equation of the regression line. Generally speaking, if the correlation coefficient represents a strong relationship, we calculate the regression line for prediction. Otherwise, we don't use that for prediction. We use the average y bar.
Find the equation of the straight line that best fits the points in the scatter plot of paired sample data. That best fitting straight line is called the regression line, and its equation is called the regression equation. The regression equation expresses a relationship between x, called the independent variable, predictor variable, or explanatory variable, and y, called the dependent variable or response variable. The typical equation of a straight line is expressed in the form of y equals mx plus b, where b is the y-intercept and m is the slope.
Equation of a line, there were three different ways, and one way is slope-intercept form. Y equals mx plus b, m was the slope, and b was the y-intercept. And more importantly, what m gave us was, if you remember the definition of a slope, it was the average rate of change of y with respect to x.
Given a collection of paired sample data, the regression line, or line of best fit, or least squares line, is the straight line that best fits the scatter plot of the data. If there is not a significant linear correlation, the best predicted y value is y bar. If there is a significant linear correlation, the best predicted y value is found by substituting the x value into the regression equation.
So we come up with the regression line. We normally come up with the regression line if the correlation is strong, in which case, if they give us an x, we put it into that and we come up with the y value. That is the prediction, if you will. And remember, y depends on x. X is the independent variable. X is the independent variable, y is the dependent variable, and so also called the predictor, for example, x, or y is the dependent variable, also called the response variable. If there is no significant relationship, there is no significant linear correlation, then we use y bar always to predict any x value. So with that being the case, there's a formula here. The formula is involved, and as you can see, somehow some of them are close to the formula for R, which means if we do the formula of R by hand, we have every component to calculate the regression equation. First, the population parameter, we use y equals beta 0 plus beta 1x. For sample, we use y hat equals b sub 0 plus b1x. In some text, and in the case of technologies such as TI, you see a and b, the value of a and b, because it is used as y equals a plus bx. Now, how do we do the calculation? If you look at the right side, the formulas are for the regression equation, and we are writing it in two different formats. Y hat is b sub 0 plus b1x, or y hat is a plus bx. I've seen that sometimes they use even y prime, by the way. So slope, or b1, you see a formula for that. N summation of xy minus summation of x times summation of y over n summation of x squared minus summation of x quantity squared. Again, pretty involved formula. What about the y-intercept, or b sub 0? We can say y bar minus b1x bar, so on and so forth. So R is the linear correlation coefficient, S sub y is the standard deviation of the sample y values, and S sub x is the standard deviation of the sample x values. You don't have to worry about this because the formula is given, but we go through maybe an example so we see how things are done by hand. Ultimately, everything is really done by technology because the process is involved, as I mentioned. So regression equations are often useful for predicting the value of one variable given some specific value of the other variable. In other words, normally x is given and you find the new y. It could be the other way around.
If the regression equation does not appear to be useful for making predictions, don't use the regression equation for making predictions. For bad models, the best predicted value of a variable is simply its sample mean y bar.
So as I mentioned before, by Bad model, what do we mean? The correlation is weak. So when you do the test of hypothesis, you don't reject H0. Then you don't use the regression line to explain anything. Good model.
They'll use the regression equation for predictions only if the graph of the regression line on the scatter plot confirms that the regression line fits the points reasonably well.
Correlation.
Correlation. Use the regression equation for predictions only if the linear correlation coefficient R indicates that there is a linear correlation between the two variables.
Scope.
Use the regression line for predictions only if the data do not go much beyond the scope of the available sample data.
We want to pay attention to the fact that if the data is covering from, let's say, I don't know, A to Z, then we stick with A to Z, not beyond the two when we want to do the prediction. You'll see in a moment. So when we do that, the concept of regression always, we see the word best fit. So best fit means that the sum of the squares of the vertical distance or residuals from each point to the line is at a minimum. So I want to explain that. So I want you to take a look at this graph and see what we are dealing with. Okay. We have the XY plane, if you will. We have the observed values. Okay, I want everybody to know what we mean by those points. Okay, those are the points and the pairs that we have the data. So we just simply plotted the given pairs. There were a bunch of it. There were 8 in this case, as you can see. Now, after we have the pairs, then we use the process and we find the regression. So the line in blue is the regression line. So for every observed value, there is a predicted value. For the same x coordinate, we have different y coordinates. Again, I want to make sure we understand what's going on. So if you look at the very first one, you have that observed value. For that observed value, this point in green is on line. So that is the predicted value of that. Second point, this is the predicted value. So on and so forth. This one, and this one. And so if you look at the red points versus the green ones, they all have the same x coordinates. So again, an observed value corresponding to its predicted value. Again, let's look at the very first pair. Those two have the same x coordinates. Let's look at the last one. Those two have the same x coordinates. So what is the difference? The difference is the y coordinates. Okay, so the distance between the two numbers along the y axis. So what is the best fit? We want to minimize those distances. So what they do, notice if the observed value is above the line, it's positive, the difference between the two. If it's below the line, it's negative. So instead of having to deal with that, remember how to minimize that. Instead of having to deal with that, they square it to get rid of that negativity. Okay, and now they add them up. They are hoping to minimize that, and they use calculus to come up with the method of, minimizing, and therefore they come up with the formula. Okay, so the idea of the best fit is to make sure those are the smallest values. Those distances are called the residuals, as far as the terminology is concerned. Those vertical distances that we are looking at, each one is a residual. Okay, so we want to minimize that. So I hope everybody understands what's going on. They have the same x coordinates. It's just the difference in y coordinates. So as far as the prediction is concerned, the prediction shouldn't go beyond the very first point and the last point. Anything in between can be predicted with the line. Beyond, when we say scope, then beyond that, it's not a good idea to use this line to do the prediction. Okay, so with that being the case, these are the formulas. The population parameter, again, sample statistics, TI, So this is the synopsis of all the formulas that were discussed in the previous page, the R, and how we arrive at the equation for the regression line. Now, when they do the regression line, it has a lot of applications. I want you to know that. For example, when colleges want to accept your application, based on the past experience, they do have a model, a regression model, not this simple. Okay, there are many variables. And basically, they pick up your information and they put your information into the model. And then it predicts the probability that a specific student can finish the program and graduate. And since they want to, keep their reputation, then they look at all of that. And on a normal basis, if it's not biased, then based on that, they decide who gets in and who doesn't. Just to give you an example of usage of this is how your application gets accepted by different colleges. All right. Here's an example.
Given the sample data, find the value of the linear correlation coefficient R. Test the claim that there is a linear correlation between the two variables x and y. Use both A method 1 and B method 2. Alpha is 0.05. Find the regression equation. Find the best predicted value of y when x is equal to 2.
This is actually complete version of what we did in the previous section. In other words, why do we do the correlation? We do it so we can come up with a regression equation and then see whether we can use that regression equation or not. Okay, so again, on purpose, I have chosen a small data, so it is doable by hand. And I can't emphasize this enough. Questions like this are not done by hand, and you're not expected to do it by hand. But let's see, since we have a small data, can we handle it? If you look at the formula for R, you can see obviously we need summation of x. So the first column x, you're gonna need to add them up, and then the y you need to add them up. Then you need summation of x times y. So you're gonna multiply those two columns, add them up. We need summation of x squared and y squared and so forth. So we do all of the above. So take a look at what we are going to do. We are going to find x times y. We're going to find x squared, and we're going to find y squared. Example, the first one would be 1 times 2, so that's 2. The second one, x squared, is 1 squared is 1. The last one is y squared is 2 squared, or 4. Okay, so you can easily see the answer. I don't think anybody has any problem with that. Again, I want to make sure that you're exposed to the methodology, okay, and how this thing is calculated. Fine, let's add them up. Let's add up all those columns. Okay, so what do we get? Summation of x, summation of y, summation of xy, summation of x squared, summation of y squared. Now look at the R formula. Plug in. By the way, believe it or not, the first one for a case like this is perhaps easier than the second one, summation of z sub x, z sub y over n minus 1, because finding z sub x and z sub y by hand takes a little bit longer. So plug in, finish the job. Now, if we had done the scatter plot, we would see that there's really not much of a relationship there. If you look at this numerically, and again, remember, we have to have precise answers, so it's important to calculate the R. This is a very small value, but when I say small, I don't want you to be okay. I don't want the negative to throw you off. This is close to 0. That's the bottom line, and that means ultimately, just by looking at that, you should recognize this is not going to work out. So when you do the test of hypothesis, remember, a strong relationship when it's larger than 0.7 or smaller than negative 0.7. A rough estimate, but you have to go through the process, because even maybe 0.65 works out. Okay, so you have to work it out to see what happens, but some numbers are obvious. So if the answer is, let's say, 0.2, obviously that's a weak relationship. So that's that. We are going to go to part B. The whole thing that is done here is simply part A. Just in case, if we were to look at the process and we don't want to do it by hand, what happens? You put it into a calculator, L1 and L2, and you have to do the linear regression test. So this will actually answer every part with the exception of D. First and foremost, notice that the p-value is 0.86, which is larger than alpha 0.05. Don't reject H0. That means there is no correlation. So that means ultimately to answer part D, we use Y bar because there is no correlation. As far as the regression line anyways, Y equals A plus BX. This is the formula that is being used everybody. So you need the value of A, which is here. You need the value of B, which is here. Everything is done for you here. So if you were to answer part A, you would see the R is here. So R is negative 0.1348399. If you were to answer part B, you look at the p-value and you say there is no correlation. If you were to answer part C, you would say Y equals A plus BX, where A is 5.4545, let's say just 5.45, plus BX, that means minus 0.1818x. And then to answer part D, simply look at the column Y. The sum is 20 divided by 4, and the answer is 5 because you're taking the average. So right here, with the technology, you're answering all of the questions, everybody. I want you to know that. Well, let's go through the process again, because you have to write this thing. So again, I want to look at both methods because I want you to be exposed to both and learn how it's done. So the first method uses T equals R minus mu of R over 1 minus R squared over N minus 2. And remember, this is always 0 comes from H0. Okay, so this is H0. Nothing is changed. Rho is 0, and rho is not equal to 0, two-tailed test. And you come up with T when you plug in the value of R that was calculated, and you end up with negative 0.1927. For method 2, you really don't have to do anything. R is calculated already, so that's your answer. So what is the test statistic? For method 1, you calculate the T value. For method 2, which uses the Pearson coefficient, you just use the value of R. What about critical value? Well, if you go with the t-test, alpha is 0.05, degrees of freedom of n minus 2, or 4 minus 2 equals 2, results in the following numbers, plus minus 4.303. What about method 2? Method 2, you use the table. You've seen the table already. Alpha is 0.05, n is 4, and the table gives you plus minus 0.950. So with that being the case, what happens now? Now we have to look at the graph and make a decision. Let's see how the graph looks like. Look at the graphs. Okay. If you look at the t distribution graph, critical values are negative, positive 4.303, and your test statistic is negative 0.1927 in non-rejection region. So right then and there, don't reject H0. If you look at the R table, then critical values are negative 0.95 and positive 0.95, and number negative 0.135 is somewhere in between. Same result. So the decision making is the same for both of them. Do not reject H0. And what does it mean? The claim is false, and more importantly, there is no linear correlation between the two variables. There is no correlation. We are going to come up with the regression equations anyways, just again to see how the calculation works. But remember, if you decide that there is no linear correlation, you really don't need the regression equation because it is not used for anything. However, for the sake of calculation, let's see how it works. If you look at the formula on the right side, okay, take a look. Y bar equals b sub 0 plus b1x, or y hat, my apologies. But it's equal to a plus bx, however that you want to put that. So let's look at this formula for the slope. Look at the formula for this slope. b1 is n times summation of xy. And remember, we have everything we want in this fraction. In the previous page, we've done that. N summation of xy minus summation of x times summation of y over n summation of x squared minus quantity summation of x squared. So take a look. We have all of that from the previous page. We put into that equation for b1 and we find it to be negative 0.182. What about b sub 0? Take a look at the next formula. B sub 0 is y bar, we have that, minus b1, we just calculated it, times x bar, we have that. So y bar is 20 over 4, x bar is 10 over 4. We have those numbers, plug in, and you get b sub 0. And now you put it into the formula, and this is the equation of the regression line. What about the answer to this question? If you recall, we said there is no significant linear correlation. The best predicted y value is always y bar, regardless of the choice of x, everybody, because r is weak in essence. Y bar is the answer. When you choose x equals 2 or 3 is there already, 4, anywhere in between, okay? Because remember, x is 1 all the way to 5 and no more. So anywhere in between, you can go with y bar. As far as the technology, remember what we did, the b, okay, I cut that and I put it here, negative 0.181818, and the a, and that's how you come up with the formula that is discussed here. The data shown is for car rental companies in the United States for a recent year. Find the correlation coefficient, the equation of the regression line, and graph the scatter plot. Okay. Again, it can be done by technology. For practice, we're going to do it by hand because it's a small data. So as you can see, the x and the y. By the way, this we had done it before, just to refresh your memory. Add up the x columns, the y columns, then multiply x by y, square x, square y, add them up. So that's what we get for those columns. And so add them up, put it into the R formula, and you probably remember that. R is 0.982. It's a strong positive relationship. Needless to say, this is normally done by technology. We have the answer here. Okay. So we got the R, the first part of the question. So find the correlation coefficient. Now, the equation of the regression. So let's move on. We already have those calculations, table calculations, all of the above is given. All you have to do, put it into those formulas. Now, when we did the formulas for the regression, there are really a couple of different ways of calculating. So let's calculate b sub 1. Just take a look at b sub 1 and plug in, and that gives you an answer 0.106. Look at the formula for the b sub 0. Last time we didn't use that one for the calculation. So take a look at the calculation, plug in, come up with the answer. Or this is what we used last time. The reason being, because when you find b1, finding b0 is easier to use y bar minus b1 x bar. So understand why I'm doing this. I want to show you both ways, both of them. give us the same answer. If you have calculated B1, probably you're better off using B sub 0 is Y bar, because that's an easy calculation, minus B1 X bar. That's an easy calculation. And why is that? Remember, summation of X is there already. Summation of Y is already there. So what is X bar? Divide by size. 6, and it's 6. Okay, remember, just divide by this number. Summation of X divided by this number is X bar. Summation of Y divided by this number is Y bar. So you pretty much have everything. This is much faster than this formula. So can you use this formula? Of course. I suggest you use the other one. Ultimately, again, if you're doing it by hand. Okay, now you put it into the formula. Y hat becomes, or Y prime, as I mentioned. So please pay attention. Y hat, Y prime, depending on the text. And I want to use all of those so you are exposed to them. 0.396 plus 0.1066. By the way, when we did the algebra, we could write the mx first. Remember, y equals mx plus b. But that's the way they write it in stats. As long as you understand the concept, you're fine. Now, using a calculator, we put the information in L1 and L2. We do the regression here, and we have the values for A and B. Okay, so notice the value for A, notice the value for B, and that's what we did with a hand calculation. You could do it either way. The next thing we want to do, we want to go with the scatter plot. Remember the formula we just came up, it's 0.396 plus 0.106x. To plot any pair, if you remember in algebra, any line in algebra, you need two pairs. All you need is two pairs. So any x value between 10 and 60 will do the job. I want to make sure everybody understands why we are saying between 10 and 60, and for example, 15 and 40. If you look at the table of data given, the table of data, the smallest value for x was 8.5. Smallest value for x was 8.5, smallest. Largest value in that table for x was 63. So the numbers really should be between those two. When we say 10 and 60, we want to be more conservative. That's the idea of scope. You can't go beyond those because your model is based on the given information, and you have to pay attention to the endpoints. So it works between those two and not beyond. So that's what we mean by scope. And so with that being the case, if you plug in 15, okay, see what happens. You get 1.986, almost 2. If you plug in the 40, you get 4.636. And you can plot those two pairs and look at the graph. Those are the points, the scatter plot. And again, you see the pairs. For example, you see 63 and 7, just as an example. This is 63 and 7. If you go back to the previous page on the table, just as an example, one pair. And here's the line. We are using the pairs to draw this line. Now, predict the income of a car rental agency that has 200,000 automobiles. Well, remember, if again looking at the table, the cars, X was in 10,000s and the income was in billions. So when we say 200,000, you really, in essence, you have to divide it by 10,000. X becomes 20, and you plug in number 20 in that formula. And why is it a good prediction? Because R was pretty strong. Everybody remembers R was 0.982, although we have to do the test of hypothesis. But it is so clear that even without the test of hypothesis, 0.982 is a good number. And we just plug in, and that gives us 2.516. Now, what does that mean? It means When a rental agency has 200,000 cars, automobiles, its revenue will be $2.516 billion. Regression, marginal change, outlier, and influential points. So these are some definitions we want to make sure we are comfortable with that. Marginal change. In working with two variables related by a regression equation, the marginal change in a variable is the amount that it changes when the other variable changes by exactly 1 unit. The slope V1 in the regression equation represents the marginal change in y that occurs when x changes by 1 unit. Okay, what do we mean by that? Again, everybody remembers the concept y equals mx plus b. What is m? M is the slope. What was the definition of a slope in algebra? Okay, the average rate of change of y with respect to x. So that slope is referred to as marginal change here. So y equals mx plus b. Okay. So when x changes by merely 1 unit, then y changes by m units, the slope. Okay. And in this case, the slope use b1. Okay. It depends whatever we're using and which text, but ultimately it is the slope. Okay. So that is called the marginal change, or better yet in algebra, average rate of change of y with respect to x, the definition of this. Okay, so as an example, okay, when this is the formula for y bar, okay, class, y bar is negative 3.37 plus 2.49x, okay. As you can see, the slope is 2.49. It's very clear the slope is 2.49 mx. It should be higher. You want to put that again. So what happens if you increase x by 1? Then the y variable, okay, the predicted variable increases by 2.49. That's the idea. I hope you see what that means. It's very simple. Replace the x with 1. So what happens? See, this negative 3.37, the y-intercept is fixed. It's not changing. So 2.49 times x, if x is 1, it gets added by 2.49. If x is 2, 2 times that, and so forth, okay? So that is the idea behind this. Could somebody read this paragraph for us?
In a scatter plot, an outlier is a point lying far away from the other data points. Influential points, IP. Paired sample data may include one or more influential points, which are points that strongly affect the graph of the regression line.
Thanks, Peter. Could somebody read the left side of the screen for us?
The scatter plot located to the left shows the regression line. If we include an additional pair of data, x equals 50 and y equals 0, we get the regression line shown to the right below.
Thanks, Mark. Somebody read the right side for us, please.
The additional point 50, 0 is an influential point because the graph of the regression line did change considerably as shown. It is also an outlier because it is far from the other points.
Thanks, Mark. And finally, what does it mean? Somebody read it for us.
Essentially, an influential point is an outlier that significantly affects the slope of the regression line. As a result of that single outlier, the slope of the regression line changes greatly, resulting in changing the shape of the line. Accordingly, the outlier is considered an influential point. All IPs are O's, but all O's may not be IPs.
Thank you so much, Dina. Okay, let me see if I can make some sense out of this. Everybody remembers the idea behind an outlier. The basic concept is something which is out there, which is not similar to the rest of the data. it's way too large or way too small. That was the basic definition. And then we showed how to arrive at that precisely using statistics, okay? And a number that was less than Q1 minus 1.5 IQR or was larger than Q3 plus 1.5 IQR. Okay, that's what we did in the beginning of the course. Okay, so we know what's an outlier as far as conceptually and as far as formula how we arrive at. So what is an outlier? What is an influential point? When we do the graph of scatter plot, every outlier can have an effect. And we know the meaning of outlier. But some of them may have such an effect that when you graph the graph of your scatter plot versus the regression line, the regression line changes so much that you can't recognize the first line anymore. So you add one pair, which is an outlier. It changes the graph so much so. In other words, how does it change the graph? It changes the slope. Now, every point you add, it does change the slope. But if it changes the slope, that the line is completely a different line. Okay, if it's a little bit off, it's just changing the slope by a little bit, and that makes sense, and that's absolutely fine. But it changes so much that you don't recognize the original line anymore. That is not only an outlier, it is also an influential point. Which means what? If you have an influential point, for sure that point is an outlier. No questions about that. But if you have an outlier, you may not have an influential point. How do you know that? I don't know. I have to check it. Okay. So if somebody says this is an influential point, for sure it's an outlier. But if it's an outlier, we must check to see if it does the same thing. Most of the time, they do. And it really depends how bad of an outlier it is. I hope everybody understands the difference between the two. So I'm going to repeat one more time. Basically, an influential point is an outlier which is really heavily affecting the graph. If an outlier doesn't do that, it may not influence it that much, okay? Most outliers do. All right. Let's look at another example.
Example 3. Given the sample data, the table lists the number of registered votes in tens of thousands. A. Find the value of the linear correlation coefficient R. B. Test the claim that there is a linear correlation between the two variables x and y. Use both A model 1 and B model method 2. Alpha is 0.05. C. Find the regression equation. D. Assume that in 2001 there were 850,000 registered votes. Because the table lists the numbers of registered votes in 10 of 1,000, this means that for 2001 we have x equal 85. Given that x equal 85, find the best predicted value of y. The number of manatee deaths from votes.
We have to go through the process of doing the work, but let's do the technology and see how fast we can come up with the answer first. Number one, look at the R at the bottom. Okay, so that's the R. Okay, so we write it. Now, number two, what does this give us? P-value. The p-value is 1.50817 whatever. E minus 4 times, that means times 10 to the power of negative 4. So if you wrote that, you get this number. This is the p-value. Less than alpha of 0.05. Reject H0. And you know the rest. When you reject H0, the claim becomes true and there is a significant linear correlation. Again, using technology, we can easily come up with the answer. Now, so we have that. What about the regression equations? Take a look. A and B are given. Okay, just plug in. A plus bx. So y hat is negative 112.71 plus 2.274 x. We're using the technology. And the last part, because the correlation is strong and because we rejected H0 and we said there is a correlation, we just simply put in other words, instead of using y bar, we use the regression equation and we plug in the value, it becomes 81. So if we have 850,000 registered votes, we expect 81 manatee deaths. So that is using technology. Let's quickly do the test of hypothesis on that again, just for practice. So if you look at the first step is identical as before, we have H0 and H1, H0 row equals 0, H1 row is not, and that is two-tailed test, that's a claim. And now you have to calculate the test statistic using the t-distribution. And for method 2 is simply R, which is 0.922 from the previous page. We need the distribution, rejection region, and non-rejection region. R stands for rejection region, N or no rejection region. And so alpha is 0.05, degrees of freedom is n minus 2, okay, which is 10 minus 2 or 8. And we come up with the critical values of plus minus 2.306. And from a Pearson correlation coefficient table, alpha of 0.05, n equals 10. And we come up with plus minus 0.632. And in both cases, as you can see, we end up with the same result. We reject H0. And so there is a correlation. And then we go through the process. We calculate this. We already have that, by the way. I just wanted to show you the test of hypothesis. And there is a significant linear correlation. We simply plug in and we end up with the following answer. 81 as we did in the previous page. Okay, so it's very straightforward. Okay, I thought it's worth looking at it again. So what happens when the correlation exists? We use the regression line for prediction. All right, let's put that to a test again. Everybody, let's put that into a test again. Here's the synopsis, if you will. If you look at the first part, it says use the table to the right, the regression line, and predict the y value when x is 10. Now, this is the formula. I hope you see the A and B, everybody. You can say A plus bx. Remember, A plus bx. That's what the technology uses. Fine. A plus bx. All right. So this is the regression line. This is a good model. We can use the regression equation for prediction. Why is this a good model? When we look at the p-value, the p-value is 4.477 times 10 to the power of minus 6. That is very close to 0. You see the 4 on the left side, you have to make the decimals go 6 places. So to the left of 4, you put 5 zeros. So the p-value becomes 0. I have put 5 zeros and then 4. And then another 4. And I'm going to stop at 7 because the next one is 7. I make it 8. This is way smaller than 0.05, which means you reject H0, which means there is a correlation, and therefore we are going to plug in and we get 21.5. But if you look at part B, predict the IQ scores for an adult who is exactly 175 centimeters tall. That makes no sense whatsoever. Okay, by that I mean there is no correlation between an IQ and the height, and therefore you use what? Y bar, Y bar, okay, and that is the mean, which is 100. So I hope you see what this page is supposed to do for us, class. This page is supposed to remind us when to use the regression line and regression equation to do the prediction and when not to. Okay, there is a correlation. There is a strong correlation. Use the regression equation. There is no strong correlation, don't. But you use Y bar. That's how we do the prediction. That's the concept.
I have a question. Where did you get the mean of 100?
It's given.
Oh, right there on B. Sorry.
Yes. IQ scores have a mean of 100 and standard deviation of 15. Okay, so in general, mu is 100 and sigma is 15. Okay, that is regression, least squares, property, and residual plots.
Least squares property. A straight line satisfies the least squares property if the sum of the squares of the residuals is the smallest sum possible.
Residual. For a pair of sample x and y values, the residual is the difference between the observed sample value of y and the y value that is predicted by using the regression equation. Residual equals y minus y hat. Residual plot is collection of pairs, x and y minus y hat. The residual plot should not have any obvious pattern. The residual plot should not become much wider or thinner when viewed from left to right.
And so basically what we are saying is that what is a residual plot? It contains pairs. What pairs? X comma y minus y hat. Y minus y hat. So here's a table, okay, a simple example. We want to find the residual value for the sample point with coordinates of 8, 4. We want to draw the residual plot and what is the marginal change. Given the table class and given the equation y hat is 1 plus x. When x is 8, part A, when x is 8, we plug in and y hat becomes 1 plus 8, which is 9. So y hat, it's simply 1 plus 8, which is 9. But what is the y coordinate? Take a look at the pair 8, 4. So y is 4. And so their difference, y minus y hat is negative 5, which means just for that 8, 4, we are coming up with the residual plot point, just 1 point, 8, negative 5. So for corresponding to 8, 4, we have this pair 8, negative 5. And so with that being the case, you can see if we can do one, we can do all. So here's the graph. I hope everybody's clear. Just look at one pair we calculated. First, y hat equals 1 plus x. That's the line. Everybody can graph it. Pick up a couple of pairs. You have it. You're done. Number one. Number two. There are 4 pairs, so we need to come up with 4 pairs for the residual plots. 4 pairs. We calculated one of them with details 8, negative 5. I highly recommend you do the rest on your own. Okay. So for example, corresponding to 12, 24, 28, 24, 32. What do we have? So it's now finally, what is the marginal change? Remember, marginal change was y equals mx plus b. So when we have 1 plus x, what is, if we are given data, the number sitting to x, come up with the table 1. Remember, x means 1x. So we have a column of x, column of y is 1. And then we need to have, if it was 1 plus 7x times y, x squared y. That would be. So we want to find those values. And then we want to add them up. Look at the synopsis of what we need to do. If
as
it is
far as
significant,
regression
how
summary
do
is
you know it's
concerned.
significant? You really have to go through the test of hypothesis. But by just looking at it, you could be able to tell, remember, 0.7, between 0.7 and 1 is a strong relationship, which is a positive one. Between -1 and -0.7, also a strong negative relationship. And in that case, you can predict using the regression line and the regression equation.